Welcome to the course on advanced machining processes. Today we are going to discuss the topic on electrochemical spark machining, which is abbreviated as ECSM process. The organization of today's talk is as follows: introduction, working principle of electrochemical spark machining process, experimental setup of the process, applications of the process. Introduction. The electrochemical spark process is used for selective deposition, welding or micro welding, and machining of conducting as well as non-conducting materials. That means, this process can be used for electrically conducting as well as electrically non-conducting materials. I would like to mention here that for electrically conducting materials, there are various processes already available, such as electrochemical machining, electric discharge machining, and some other processes, but very few processes are available which can be used for machining or microfabrication of electrically non-conducting materials. So, this process is an unique process which can be used for electrically non-conducting material, and it is the hybrid process, as I will discuss little later, which combines ECM process and EDM process, and both these ECM and EDM processes are useful only for electrically conducting materials, but the hybridization has led to its hybrid process utilization for electrically non-conducting materials. It is potentially useful and novel process for rapid prototyping also. It is important to understand the mechanism of spark discharge formation and hence the material removal, as the name indicates that spark is responsible for removal of the material. That means, it falls in the category of thermal process. Evolvement of electrochemical spark, as you can see here, branch in the classification tree of manufacturing process. You can see here the classification of manufacturing processes, like change the shape of material, machining of parts to a fixed dimension. Here you have traditional and advanced both. In terms of advanced, you have mechanical type, thermoelectric type, electrochemical and chemical processes, as you can see here, and then you have the hybrid processes, and electrochemical spark machining falls in the hybrid process. We are not going to discuss finishing processes or joining processes or changing physical properties processes. Now, let us understand the working principle of electrochemical spark machining process. How electrochemical spark machining works? In ECM, as we know, hydrogen evolution takes place at the cathode in the electrolytic cell, and this takes place if high current density is there between the anode and cathode, then sparking takes place across this hydrogen bubble which is evolved at the cathode. However, we know that this is not a desirable phenomena in case of ECM, because it is going to damage both tool as well as workpiece, because in ECM the material removal takes place by electrochemical dissolution, not by sparking phenomena. Now, the question arises, can we make constructive use of this phenomena, that is sparking phenomena, like what we have in case of electric discharge machining process, where spark is being used for the removal of the material, and this EDM process gives good dimensional accuracy as well as good surface finish. Then the answer to this question is yes, we can make constructive use of this spark, which takes place across the hydrogen gas at the cathode. It can be used for machining electrically non-conducting and electrically conductive materials. For this purpose, keep the workpiece close to the tool near the spark, because spark is taking place at the cathode, that is the tool. So, keep the workpiece near the cathode, then it will work like EDM process for electrically non-conducting as well as electrically conducting material, because in EDM also what we are doing, we are having the spark across the two electrodes. One of those electrodes is workpiece, another is tool. So, since workpiece is so close to the tool, so close to the spark, or the spark is taking place on the workpiece itself, so that heat which is evolved due to sparking is responsible for removal of the material in EDM process. Same phenomena takes place in electrochemical spark machining. If we keep the workpiece very close to the spark taking place at the cathode. What is electrochemical machining? Newly developed hybrid process for machining electrically non-conducting ceramics and composites. So, it should be what is electrochemical? Spark machining, not electrochemical machining. And you can see here electrochemical spark machining ECSM is hybridization of ECM process and EDM process. This figure indicates the working principle of electrochemical spark machining process. You can see there is a machining chamber, and in this chamber is filled with the electrolyte. You can use various kind of electrolytes as we have discussed in case of electrochemical machining process. And then you have a anode which is of quite large size compared to the cathode as shown over here. Now, you can clearly see this, there is a big difference in the size of the cathode as well as anode. Now, what is happening as shown here, that bubbles are generated, as you can see bubbles are generated at the cathode, and due to high potential gradient across the bubble sparking takes place, and you can see in the side left figure shining spark has taken place over there, and this is the picture of actual setup where sparking was taking place. So, this sparking takes place across the bubble on the cathode, and the workpiece is kept very close to the cathode, so that whatever heat is generated in the spark, part of that heat is transmitted to the workpiece, and this heat is responsible for melting and or vaporization of the workpiece material, and this is exactly the same principle as that of EDM. Now, when melting or vaporization takes place, you can get the replica of the tool in this particular case also, that is electrochemical spark cutting or drilling process. So, it shows a schematic diagram of basic electrochemical cell. This is called as electrochemical cell. Now, this is another picture of the same electrochemical spark process schematic. This is the electrochemical cell, electrolytic cell. Again, anode is there, cathode is there. The gap between the cathode tip where a spark is created and the workpiece top surface is around 500 micron. Now, you can see here that workpiece is neither cathode nor anode. So, it can be electrically conducting material, it can be electrically non-conducting material, and discharge is taking place very close to the workpiece. That is why the heat generated in sparking is transferred to the workpiece, and that melts and vaporizes the workpiece material. Now, there are certain chemical reactions that are taking place at the cathode. Electrolysis takes place, and you have 2 H2O plus 2 electrons, you get hydrogen gas which is evolved over here, across which the sparking is taken place, plus 2 OH ions. At the anode, oxidation takes place and 4 OH they form 2H2O plus O2 plus 4E. Now, then there is further dissolution of the material from the cathode. So, we do not from the anode, and we do not want dissolution of the anode. So, we can use such kind of anode material which does not dissolve in this particular configuration. Normally, the anode is made of graphite. Now, in electrochemical spark machining, there are various modes of material removal. One is the melting and vaporization, which I have explained with the help of couple of figures just now because of the spark heat. Chemical reaction is also taking place, which is also responsible to some extent to remove the material if proper electrolyte is not selected. Cracks propagated by random thermal stresses, because temperature is very high in a very localized area. So, there is very high temperature gradient, and because of this very high temperature gradient, thermal cracks are produced in the machine workpiece, and that leads to the defects in the workpiece if proper machining conditions are not set. Then mechanical shock due to cavitation effect is there, and this also may lead to some extent the removal of material from the workpiece. There are various process parameters. The most important process parameter is supply voltage, and the value of this is normally kept 35 to 50 volt or even more than that, depending upon whether you are working on micro machining or you are working on macro machining. Now, you can see here the difference in electrochemical machining. Normally, the voltage capped is 5 to 30 volt, but in this particular case where you are creating the spark at the cathode across the hydrogen bubbles, you are keeping the voltage 35 to 50 volt or more than that. Copper tool is normally used in some cases, not in all cases, and of around 200 micron diameter wire can be used as a tool. Workpiece material, in this particular case where some experiments were conducted at IIT Kanpur, soda lime glass was used as the workpiece material. It is electrically non-conducting material. Water to workpiece to glass gap between the workpiece surface and the tip of the tool, that was around 50 micron. It can be more than that also, as I mentioned in the earlier slide, around 100 micron. It can be even lower than this, depending upon for what applications you are using this particular process, whether macro or micro material removal. Sodium hydroxide has been used as the electrolyte, and the concentration was varied from 14 to 20%. In micro machining, you can go even lower than this concentration. Table speed, because the motion is given to the table, so that you can create a certain kind of the features on the workpiece. So, it is given in the RPM, but better way to represent the table speed is in terms of millimeter per second. Bare length of the tool protruding out from the tool holder is around 4 millimeter, because if you see, as you will see in the setup, there is a tool protruding outside the tool holder. This is the tool holder where wire is held. So, this length which is protruding outside the tool is shown here as 4 millimeter, although it is very large. Normally the length of the tool protruding, bare length of the tool protruding outside the tool holder should be lower than this. Otherwise, in drilling it will create a tapered hole. How microfabrication can be achieved with electrochemical spark? So far I have been talking about to you about the electrochemical spark used for machining purposes. You can use it other than machining purposes, as I mentioned earlier. You can use it for the purpose of deposition, you can use it for the purpose of welding as well. Heat generated by the electrochemical spark can be used for machining as a subtractive process, as I have explained, conducting as well as non-conducting materials, both can be machined by this particular process. Then you have the deposition, that is the additive process. Selective deposition can be done. Then you can also use it for micro welding purposes, and people have proposed to use this particular process for rapid prototyping of metallic parts. Although in the deposition process not sufficient progress has been made, as long as additive process or versions of additive process like selective deposition, micro welding, rapid prototyping are concerned, but research work is going on in these directions also to make use of it, because this process has got certain advantages over the conventional rapid prototyping processes. Experimental setup. You can see here, this is the schematic design of machine setup which was developed for deposition purposes. Here you can see XY table is there, XY table, tool feed assembly is there, jet assembly, workpiece table, electrolyte supply system, control station, etc. you can see. And apart from that, it was also designed for rotating the workpiece in x direction along the x axis as well as along the y axis, and this setup was developed for micro fabrication purposes. This is the actual photographic view of the setup that has been fabricated at IIT Kanpur. Now, working principle is the same as I have already explained. Here is the anode and here is the cathode, and these are the hydrogen bubbles across which the discharge is taking place, and near to this discharge you can see the workpiece is there, and because of the proximity of the workpiece to the spark, material is removed by melting and vaporization from the workpiece. You can clearly see the spark being created across the cathode and near the cathode rather on across the hydrogen bubble, and you can see the shining picture of the spark. The main components of electrochemical spark setup are machining chamber, as you can see over here in the top left hand side picture, ECS cell, exhaust system is there, because whatever gases are evolved during electrochemical spark machining, those gases should be exhausted outside, otherwise they will be harmful for the operator, people standing near the setup, as well as the machines that are near to the setup. They will get corroded if the exhaust of the fumes is not done properly. You can see on the back side there is a exhaust system which is not clearly visible, and this takes out, exhaust fans are there, 2 fans are there which will take out the fumes developed in this machining chamber during electrochemical spark machining. Control of the system is done with the help of the PC. And then you have power supply system, you have separate power supply for machining and separate power supply for moving X, Y and Z stepper motors. Now, there are various applications of this particular process. Now, this electrochemical spark grinding process was also developed at IIT Kanpur, and you can see the tool, instead of plain wire as the tool, the copper or brass tool was used, which was having abrasive particle embedded on it, and these were the alumina abrasive particles. So, when this tool is rotating and electrolytic cell is formed, you can see anode is here, cathode is there, and they are kept away from each other, and then 0 to 150 volt is being applied across them. As a result of that, hydrogen bubble is formed on the metallic part of the tool. So, that metallic part of the tool where hydrogen bubble is forming, that spark king takes place, and the spark softens the workpiece surface, and part of the material is removed due to sparking, and some part of the material is removed due to the grinding process, because abrasive particles are also in contact with the workpiece surface, and when you are rotating the tool, then this is removing the material due to grinding process or with the help of the abrasive particles which are protruding outside, as well as due to the spark. And you can see here in the picture, it is showing the sparking taking place, and this is the abrasive particle in contact with the workpiece surface. This is the workpiece surface over there, and here it is clearly written graphite rod is used as the anode, because it does not dissolve during electrolytic process. You can see here enlarged photograph of abrasive cutting tool showing abrasive particles and base material. These are the abrasive particles which are in contact with the workpiece. Enlarged view of this particular left hand side setup is taken. Electrochemical spark cutting of Kevlar fiber composite. This particular process is basically used for electrically non-conducting material, and Kevlar fiber composites also electrically non-conducting. So, you can see this electrochemical spark machining has been used for cutting the Kevlar fiber as shown over here. Now, when you are using this particular process for glass fiber composite materials, there are certain problems, because the melting temperature or softening temperature of the glass is very high compared to the epoxy matrix. So, when sparking takes place near to the workpiece surface, the epoxy gets eroded or removed, and the protrusion of the part of the fibers remain intact over there. So, you really do not get a good surface when you are using electrochemical spark cutting or machining for glass fiber composite epoxy composite materials. So, these are some of the problems which have to be solved before applying it for machining glass fiber epoxy composite materials. Electrochemical machining of alumina, quartz and composites. Some of the specimens that were machined at IIT Kanpur are shown here in this particular figure. You can see the ceramics which has been machined. Here some conditions are also given, 50 volt. Then here also again you can see other type of the ceramics, they have also been machined. Especially trepanning kind of operations were tried over here, that you can see clearly in this particular case. Then quartz was also machined, and you can see various components where trepanning was tried, and you can see clearly the holes that were drilled by the trepanning operations, and some blind holes also have been made in case of the quartz. Then you can see here the glass fiber composites, a slot was cut or channel was cut as visible over here. Then this is the another example of the glass fiber, and these are the Kevlar fiber composites where hole drilling and channel cutting have been done with the help of electrochemical spark machining process. So, what does it mean? That it can be successfully used for creating various kind of the features on electrically non-conducting materials like ceramics, quartz, glass epoxy composites or Kevlar epoxy composites. SEM photographs of the pits formed on the edge of the tool. Now, you can see, because as I mentioned earlier, that sparking is taking place between the or across the hydrogen bubble, and these hydrogen bubbles are evolved at the tool on the metallic part of the tool, not the abrasive part of the tool. So, you can clearly see that metal that is being removed is in the form of circular pit, and this is due to the sparking taking place on the tool. SEM photographs of the tips of Kevlar fibers showing the ends of the cut fibers thermally deformed. As I showed you in the earlier slide, that glass fiber epoxy composites are being machined using electrochemical spark machining. Now, what happens to the glass fibers at the tip? You can see that melting or softening of the glass fibers was taking place, and you can see the tips which are not sharp, rather they are rounded, because the softened material or molten material has resolidified over there itself. So, this clearly indicates the fact that this is a thermal process taking place. Now, blind hole in quartz at 65 volts during 4 minutes machining with eccentric rotating tool at 20 rpm. You can see the cleanliness with which the blind hole has been made in the quartz. Now, a magnified SEM photograph of a pit, and that indicates that the material is removed, and it also gives some idea what kind of heat source it is. To me, it looks that it is a Gaussian heat source, and more amount of material is removed from the center and less amount is removed from the edges. This is another example of through hole machine in borosilicate glass tube of wall thickness in 8.45 minutes at 65 volts with 25% NaOH as the electrolyte. Solid eccentric rotational tool is used. So, this has been cut as a hole. An enlarged view of showing thermally damaged zone and resolidification on the wall of machined surface. You can clearly see the damage that has taken place on the sides or on the top surface of the workpiece due to the heat source. So, we have been able to machine quartz, glass, silicon, copper also, and tantalum as well. So, some examples will be shown to you about the cutting of glass. You can see here the micro channel. This is the enlarged view of the micro channel formed on the glass. This is the enlarged view of the micro channel, and you can see some of the globules shown over here, but some of the non-globular form material is also shown. That means, due to the micro crack, some material got removed from the parent material, and that is what is shown over there. But at most of the places you will find globular form of the material, because whatever is the molten material or softened material that gets solidified, and naturally it is going to be in the form of a sphere. This is the another example of a micro channel formed with the help of electrochemical spark machining process, and you can see the size width of the channel is 643 micron and length is 1348 micron. So, it is around aspect ratio as 2. Now, this is very peculiar, very interesting figure or that has been made at IIT Kanpur by Anjali Kulkarni during her PhD work. The complicated channel has been created in the shape of 8, as you can see over here, and this is quite accurate as long as width is concerned and uniformity of the diameter is concerned. And the conditions are at 50 volt this was machined. Now you can see here the enlarged view of the channel. Now, this is a thermal process, and you can see lot of cracks are formed on the machined surface, and these kind of the cracks are not acceptable in real life product. So, one has to optimize the parameter so that the cracks etc. are eliminated during formation of the channel or groove or the hole. You can see further enlarged view, and clearly you can see the cracking of the top surface or machined surface. Again further view of the glass microchannel form and cracking taking place on the machine surface. This is another view. Now, here is the silicon. You can clearly see the structural difference between the glass channel and the silicon channel. Here those kind of the cracks are not observed in case of silicon channel as were observed in case of glass, and this is basically due to the difference in thermal properties, mechanical properties and physical properties of these two materials, that is silicon and the glass. Now, again silicon, you can see the cleanliness of the channel formed in the silicon workpiece. However, there are some debris that are also seen in this particular case, as you can see here within the circuit, and all these channels have been formed with the help of electrochemical spark machining process, as I have explained to you. Then metallic pieces were also machined and the holes were drilled, micro holes were drilled, and you can see when you are drilling the hole, the size of the hole at the entry and size of the hole at the exit will be different, and that is what we have tried to show here. This is the copper and this is the entry side hole and this is the exit side hole, and we had used here pulse power supply, and you can see here pulse power supply and resulting current that were observed during the process. Then tantalum material was used as the workpiece, and using the electrochemical spark machining process we have drilled the hole on the tantalum, and you can see the roundness of the hole in all the three cases. This is very small holes, 60 micron, this is 300 micron and this is 440 micron holes drilled with electrochemical spark drilling process, and these are the electrically conducting materials. So, we have been able to make use of this particular process for electrically conducting materials as well as electrically non-conducting materials. However, this process was basically developed for electrically non-conducting materials. So, the ECSM process is useful for selective deposition, micro welding, machining of conducting and non-conducting materials. Device fabrication can be done with the help of this process. The array of micron size probes, embedded sensors. There are various traditional micro fabrication processes like IC fabrication, bulk micro machining, surface micro machining. ECS based micro fabrication, the present method will be different from the traditional micro fabrication process. There is no need of high vacuum that you normally use, whether it is the ion beam machining or deposition or electron beam machining or deposition or other processes. It is cost effective, simple, definitely it is multidisciplinary. The fabrication facility will open up the research avenues in the field of automobile, electrical, manufacturing and similar other areas. You can see some of the basic research that was conducted at IIT Kanpur by Anjali Kulkarni is that the recording of the current during electrochemical spark machining process and simultaneously measurement of the temperature variation with time. So, we can draw following inferences that the discharge in electrochemical spark is similar to the discharge in a gas due to the application of high electric field. The electrons generated in huge number due to the discharge accelerate towards the workpiece kept near the cathode tip, the former being at a relatively higher positive potential. This flow of huge number of electrons is seen as a current spike for a short duration of a few milliseconds. This bombardment of electrons raises the temperature of the workpiece momentarily, giving rise to a sharp temperature pulse as seen in figure in the earlier slide. As seen earlier, the temperature reaches to melting and evaporation points and material removal takes place due to the melting as well as evaporation. Thank you very much. Now, Mrs. Anjali Kulkarni is going to explain you the experimental setup, some more applications of the setup and how various elements of the setup have been fabricated. Thank you very much.
Good morning. You are welcome to the Manufacturing Science Lab, and we will be shooting about the experimental setup that is a part of series of Professor V.K. Jain's lectures on advanced machining processes. Here you will be introduced with the electrochemical machining processes in general and electrochemical spark machining process in particular. This is the schematic of the electrolyte cell. There are two electrodes, one is anode, other is cathode, and a workpiece which is a separate entity placed nearby the cathode tool. The cell is filled with the electrolyte. Normally we use a diluted solution of HCl or sodium hydroxide. And in ECSM particular, unlike ECM, the tool sizes are different, means they are grossly different in size. Anode is of larger size and cathode is of smaller size. This ensures the sparking at the tool tip and between the interface of the tool tip and the electrolyte. A supply is given, and when the supply is given in this polarity, negative to cathode and positive to anode, then two electrochemical actions take place. These are called redox. At cathode you will see the reduction action by water molecules combine with the electrons and they evolve H2 gas near the cathodes, and at anode the oxygen gas liberates. This is the setup which we have developed at IIT Kanpur. This is about the microfabrication using electrochemical spark. This process or this project is sponsored by DST, Department of Science and Technology. This is the machining chamber of the electrochemical spark machine used for microfabrication. This is the XY stage which are motorized using stepper motors and guide rails for the travel. This has total travel of 100 mm with an accuracy of 1 micrometer per step. The XY are both similar in size. Bellows are used to protect them from the electrolyte environment. This is the Z axis. The total assembly is made of aluminum and brass to avoid the corrosion due to electrolyte. A separate stepper motor is used to drive this up and down. A 1:38 gear ratio is used to transmit the power. Again, this motor is interfaced to the control station. On the Z axis we are seeing this is the tool feed assembly which is mounted on the Z axis. This has got separate stepper motor. This again is interfaced with the control station using control card, National Instruments control card. So we can activate X, Y, Z up down and tool feed. A provision is also made to have the workpiece rotation and tilt in workpiece, which right now is dismantled, but that again is interfaced so that we have 6 degrees of freedom machine. And here this machine, though it is fabricated for spark machining process, with the change in electrolyte and with the change in power supply and the scheme, this same can be used for electrochemical machining, electrode discharge machining by using kerosene as a dielectric in the electrolyte cell, and for electrochemical spark machining. This is the control station. And all the 4 motors, those are interfaced to a National Instruments motion control card, that is a stepper motor control card, and here you can have a look at the program. With this program we can move the XY stage, the Z assembly or the tool feed. We can change the RPM or the velocity, and we can give number of pulses to move in a particular distance. I will show you how it is controlled. I will show you the motion of each and every axis via this control card. One can see right now the Z motion. I am programming it. So here is the single axis motion mode. Axis 8 is configured to the Z axis assembly. We are using open loop control. There is no feedback from the stepper motor as such. The velocity I am setting it as to be 20 RPM. This is the control program based on LabVIEW platform. LabVIEW is a software. Description is as Laboratory Virtual Instrumentation Engineering Workbench is the acronym as LabVIEW. Here we have used stepper motor card, that is NI7358, which has got 8 axes, meaning we can control 8 motors. Here we are using 6 motors, and all those 6 motors are different types of stepper motors. Those are all interfaced to this control card. Here one can see this is the configuration of the card, and here one can see the devices, hardware's interfaces. So this gives you the default settings for axis 1, 2, 3 to 8. We have axis 4, 5 connected to encoders are enabled. This is the feedback is not there. This is a stepper motor. So likewise we have configured for all the axes. Axis 5 is also configured, and there are different default settings. We can move axis 4 in the interactive mode. So I will go to now to the interactive 1D, or I can go to 2D interface mode. Here I will change the definition as axis 5 is configured to the X axis and axis 6 is configured to the Y axis. So in this mode, if I move axis 5 and axis 6 both together, in this 2D interactive mode we can have different type of contouring actions. So we can go to circular mode, which we have used in our work on making the microchannels in the shape of 8. So here what we are doing is that axis 5 and 6 are configured in the circular mode. We can change the velocity. We will go to small velocity. This velocity is in RPM. This results in 1 RPM of X axis results in 5.55 micrometers per second. I will show you how the control station gives me the contouring possibility. I am starting the motors. Configuration has taken place. So this same will be followed in the XY stage, and we can have a machining in the circular nature. So this is about the contouring function of the control station. I am going again to 1D interactive mode. Here I can show you working of each single axis. So I am setting now to X axis. and we will see the resultant in the XY stable motion. Now one can see the y-axis is rotating in the counterclockwise direction, and though the actual position cannot be seen over here, the axis stage is advancing forward. I can show you now the change in direction. Now you see the motor is moving in the opposite direction. Now I am showing you the motion of Z axis. I have configured here for axis 8, which is connected to Z axis. The velocity I have maintained is 20 rpm, which will correspond roughly to 1.6 micrometers per second, and the negative direction will show it going upward, as you can see over there. So this is the Z axis, so which is taking the Z assembly up by 1.6 micrometers per second rate. I will show you the opposite direction motion by configuring the position and changing this position sign. One can see that the motor is moving in the opposite direction, and that Z axis is taking this Z assembly at the lower position. The accuracy of this is 50 micrometers per pulse. So we can set the gap between the tool and the workpiece by taking the Z axis assembly and by adjusting the tool feed also. Now in the control program I have configured for axis 2, which is connected to the tool feed. So one can see over here that this motor is moving, and the result can be seen in this mirror over here. So this was how the XY stage, Z axis and tool feed, they work via the control station. Here one can see the electrolyte fumes while the machining is going on. Electrolyte fumes, they come out, and those need to be taken out from the setup to avoid the corrosion. Here one can see a hose which is connected. This takes the fume away, and there is a exhaust fan over there that quickly removes the fumes. So after seeing the operation of how the stages move, we will now set up the experiment. Here you see here the electrolyte cell is there, which is comprised of a beaker. This is filled with 14% of NaOH. These NaOH pellets look like this. We weigh on the electronic weighing machine. So for making 14% NaOH solution, we have to dissolve 14 gram of NaOH pellets, 100 gram of water. So this is how the solution is prepared. We fill the beaker with the solution. One can see here the workpiece mounting stage. This is the tool wire coming out. A glass tube is provided to avoid the stray current effects. There are two electrodes. This is cathode passing through this glass tube and protruding out here. This glass tube provides the protection from having the stray current effects. This is the anode, which is a graphite anode whose resolution is very less. This is inserted in the electrolyte. A gap of 3 cm between the cathode and anode electrode is maintained. Then a glass workpiece in the form of a cover slip is mounted, which is not very visible, and the electrolyte level on the top of the workpiece is maintained around 1 mm. The level we ensure with a With the measurement, we have used a small piece of scale and we see the level over there. Then we maintain the gap between the tool and the workpiece surface with the help of the Z-axis assembly that makes the coarse arrangements, and for fine arrangements we use tool feed mechanism. So in our experiments we maintain a gap of around 50 micrometers between the workpiece and the tool wire. We have different kinds of standard materials of standard thickness. We use those to see the gap. Here now the gap is less than 60 micrometer. The power supply to this cell is given with this unit. This is a DC power supply unit. This changes from 0 to 60 volt and its current capability is of 15 amperes. These are the wires which are connected to the electrodes. I will show you now by connecting the DC supply how the spark occurs at the tool tip. I am varying the voltage slowly, gradually. So this is occurring at the tool tip and the surrounding electrolyte. This energy of the spark is utilized for carving the microchannels in different shapes. So here 4 samples are placed, 2 are glass workpieces and 2 are silicon workpieces. These are treated at 50 volt DC supply between cathode and anode. Cathode is 200 micrometer copper wire, anode is graphite rod, and 2 small channels are there. These need further magnification to see properly. That is why we have carried out scanning electron microscopy to study these channels. These are 2 silicon pieces, and on this workpiece there is a circle which is formed, and on this workpiece there are 2 complex microchannels are formed. As I have shown you on the control station that we can use XY contouring mode and we can have the microchannel in the form of circle, or in the modified way we can have the 2 circles side by side creating a complex shape, a kind of infinity or 8 we can say. So these channels are formed on the glass and on silicon. The photograph on the right shows the surface topography of the microchannels. These are studied using electron microscope. The image can be seen at 332 magnification, and one can see how the surface is looking due to the heat affected. This is another channel formed on silicon. This is a part of the channel studied under scanning electron microscope. The pits are seen. So this is the microchannel, and the 2 regions on the 2 sides, these are heat affected zones.